Welcome to solverfy.
We're asked to prove that the centroidal polar area moment of inertia of a given area A cannot be smaller than a squared all over 2 pi. This is actually a extremely difficult problem, and depending on what they mean by prove, you probably don't have the math background to actually prove it. But and the answers that I've seen in this problem all basically use a lot of hand waving. So I will try to show you a couple ways to convince yourself, and then actually the way to solve it properly. So what we have here is we have the change in the polar area moment of this blob here, this unknown area, and that is given by this expression here. If r is a function of theta, which actually is an assumption because we could have a blob where r is not a function of theta if it came back in on itself like that. Then we'd have to go do some other methods. But this isn't a completely general case, but if r is a function of theta, that's basically that for any ray coming out of here, we only cross the surface border once. Then we have this expression for the difference. Okay, so then we can say, well, the areas have to be the same. So this is the area of this unknown area, or unknown region, and this is the area of the circle is pi r squared. So we can say that, okay, r squared, then we can get r to the fourth, which we need up here. So r to the fourth is 1 over 4 pi squared times this integral here, squared. Again, an integral of a function squared over some finite region is going to be positive, and then square this is going to be positive. So obviously we get a positive value for r here. So that would be the radius. If we wanted to calculate what the radius is of the circle, we could use this formula here if we knew what r of theta was. But what we can do is we can use this in here, and what we get is 1/4 the integral from 0 to 2 pi over r of theta to the 4th power d theta minus 1 over 8 pi times this integral 0 to 2 pi r of theta squared d theta squared. And there's actually a proof. There's actually a proof in mathematics that you can show that this is in fact bigger than this. So if you integrate the 4th power of a function, it's going to be bigger than, again, 1/2 pi times the integral of this function and then squaring it. Okay, and obviously one thing that you can't do is you can't just pull this square into here and say that 1 over 8 pi is less than 1 over 4, and with these things being equal, because obviously we can take a function and take the square of a function and integrate it, and then take that value squared is not the same as taking the 4th power of the function and integrating it. So that's kind of a hand wavy way to do it, and you can check for yourself, plug in some various functions into here and see that this is always true. Another way of doing it, a little bit different, is to assume that that r of theta is the mean radius plus some small thing times some difference function, delta theta. if we do that, what our area constraint says, if we say that the area of this that's bounded by this region must be pi rm squared, we get this formula, which says that the integral rm times the integral of delta theta plus 1/2 epsilon times the integral of delta theta squared equals 0. Or we can get a relationship between the integrals of what these functions are. If we're given Rn, then we have a relationship between what the integrals of these functions can be. Note that this thing is always positive. If epsilon is positive, then this thing must be negative because this is positive. So we can, what I did here is instead of writing these integrals out all the time, I called this one I1. So I1 is the integral of delta over from 0 to 2 pi. I2 is the integral of delta squared from 0 to 2 pi. So we get this relationship here that I1 must be equal to minus epsilon over 2rm times I2. Now, if we expand out if we plug this into our formula for the polar area moment and expand it out in powers of epsilon, okay, so we just have this thing to the fourth, and we can do the math to expand that. We get this is 2 pi pi over 2 rm squared over to the fourth. This is also equal to a squared all over 2 pi if you use the relationship between a and rm. And so then we have this term here where we have this integral, and then we have this term where we have the integral of delta squared, then we have an integral of delta cubed and an integral of delta to the fourth. All right. So what we can do here is take this, let me actually make this a little cleaner here. This is Rm epsilon to the third power. But we know from our area constraint that that has to be true. So we plug that into here. And what we see is that the polar area moment is the area moment of the circle with mean radius Rm plus some terms here. And notice that this term has to be positive because the integral of a function squared over some finite range is positive, because this is always positive. So if you integrate it, you're going to sum up a bunch of positive numbers. So this is positive, this is positive, this is positive. So to leading order when epsilon is small, we get the radius, polar area moment of the circle with the radius Rm plus some positive number. So that means that this has to be bigger than this. Now as epsilon gets bigger and bigger, we could say, well, what happens? This could be negative here. This has to be positive. Well, this will always, even if epsilon is large, bigger than 1, this thing is always going to wind up being positive also. So we have our base polar area moment plus some positive number. Now, to actually prove it, you need to use a thing called calculus of variations, which you probably are not aware of. And the calculus of variations basically takes what's called functionals. Let's actually do a little thing here. So a functional, a lot of times we'll denote it by, say, a script I, and it's a functional is a function of a function. So we say we put a function in here, so it takes a function and it spits out a value. And you've seen this ever since you started doing calculus, because any definite integral is a functional, because it takes, you give me a function and I'll give you a value, and you give me another function, I'll give you another value, another function, another value. So a definite integral is just a functional. It takes a function and spits out a value. The difference between a function and a functional is a function takes a value and spits out another value. A functional takes a function and spits out a value. So what we have here is the area, the polar area moment is a functional of r. You give me a function r, and I can tell you as a function of theta, and I can tell you what the polar area moment is. Give me another function, I'll tell you what it is. So you give me a function, I'll give you a number. And so what we want to do is we want to find r, the r here, that minimizes what number I get. So you keep giving me functions, I keep giving you numbers, and you keep giving me functions, and finally you find out, oh, this one's got to be minimum here. Okay, so our minimum is here. And what function is that? What function minimizes this integral? Now, we obviously, one thing we could say, well, if we don't have any constraints, that, well, this thing, well, could be 0. R is 0. Well, that minimizes everything, because that then gives us a 0 here. But we need is a constraint, and that constraint is that the area has to be for a fixed area. So we have a constraint that the area is a naught, and that equals the integral of r dr d theta. So that's our constraint. We have to have, given me an area, then I can find, give me an area, and then let me find an r that has a region surrounded by r of that has that area that then minimizes the polar area moment. And the calculus of variations, what we can do is when we have a constraint here, we can put a Lagrange multiplier here and add the constraint. Okay, so we know that now we have an unconstrained minimization problem, since we added our constraint into the minimization problem. And we know this, so now we need to find a function that minimizes r cubed minus lambda r over the area of the region surrounded by r. And lambda is an unknown. So what we can do, though, is the calculus of variations basically tells us how to minimize this thing. And it turns out that it looks, if you have simple functions like this, it looks a lot like calculus. So we want to minimize this functional, I call it f of r, over all functions r. And we do that, we use this little delta symbol here to say the variation of the functional r must be 0. Okay, so it's like setting the derivative of a function to 0 to find an extrema. And the variation of this functional actually is 0 only when the derivative of this with respect to r is 0. So that says that we need that r equals 3r squared minus lambda must be 0. Okay, so this whole step here is all about calculus of variations, and you can take a math class on that probably in grad school. But what this tells us is that r squared and lambda is a constant, so r squared must be a constant, so r must be a constant. So that if we're given an area, okay, we can find the radius, okay, the circle enclosing that area, and then we know that their polar area moment is that. So we know that basically, given an area, we can find an r, and then that r, we can find an r that has a circle that encloses that. So r is a constant, and r is a constant here. So we know that it's actually given an area that we surround it by a circle, given a value for our area, if we surround it by a circle, then that has the minimum polar radius of gyration, polar area moment of any region with that area.